As we learned in the previous set of slides, reaction order puts reactants in order of increasing effect on the reaction rate. So it allows scientists to understand if I increase or decrease the concentration of certain individual reactants, how is that going to affect the rate? We're going to start with a practice problem on trying to figure out reaction rate and the influences of certain reactants on a reaction. So the chemical equation and the rate law for the thermal decomposition of dinitrogen pentoxide is given. So I've got 2NO2O5. It's going to decompose to produce 4 moles of NO2 plus O2. The rate is given, K times the concentration of N2O5. What will be the effect on the reaction rate if the concentration of N2O5 is raised from 1 to 3? So you would put this concentration into the formula here. Okay, so if I just had a 1 there, it would be a 1. If I had a 3 there, it would be a 3. So we say that the rate of the reaction would increase by a factor of 3. That's a pretty basic one, so let's see if we can practice a harder one. Oh, sorry, I forgot the top one. If changing the concentration of something does not affect the reaction rate, we say it has 0 order, or it doesn't really belong as an influencer. So let's look at another problem. I have a chemical equation and a rate law that's given. Nitrogen monoxide gas with bromine is going to produce 2 moles of NOBr. The rate is given to us, so we do not have to figure that out. We don't question it. That's just what's given, and that's how we know the rate law. And it asks us to figure out what the effect on the reaction rate will be if the concentration of NO is raised from 1 to 3. Okay, so notice that that one is squared. Okay, so if I put 1 squared, now we don't know the concentration of Br, but in this case it doesn't really matter, right? That's going to be 1. If I do 3 squared, that's going to be 9. So we say that that reaction rate will increase by a factor of 9 simply by increasing the NO concentration. All right, so as we talked about reaction mechanism or reaction process with the analogy of washing your clothes, in chemistry there are a lot of different steps that have to happen for a product to be produced. Now, we learned when we studied gases that gases are going to collide with each other. This is known as the collision theory. Okay, the collision theory tells us that molecules, atoms, and ions are going to collide with other molecules, atoms, and ions in order to react. Okay, since only 2 particles can really come into contact at the same time, that helps to explain why reactions take place in steps. Okay, if you have 3 reactants and only 2 of them can collide in order to produce a product, then it's going to make an intermediate, and then you're going to have to do it again in order for that 3rd reactant to react. Okay, if you need 2 molecules of one reactant to collide with 1 molecule of another, that's going to be pretty difficult. Okay, one molecule of a reactant reacts with the other to form what we learned a few slides ago to form an intermediate. Okay, so here's the example again of ozone. Notice that this oxygen here is the intermediate that gets consumed again, but the overall reaction is 2 molecules of O3 to produce 3 molecules of O2. Okay, because these cancel out. It gets produced and then consumed in the 2nd step. Well, what does this have to do with reaction rates? Okay, well, we're talking about collisions, and we're talking about effective and ineffective collisions. If you recall when we learned gases, effective collisions are ones that lead to the formation of products. Ineffective collisions do not. Okay, most collisions are ineffective. You have to really collide at just the right orientation in order for it to produce something. Okay, so here we have a series of different collisions. They have to collide with enough energy and in the right orientation in order to produce a product. So the orientation of the particle and the energy behind it is necessary to break bonds and form new ones. Okay, and if you recall the two types of energy that we learned way back when at the first quarter, potential is stored energy, kinetic is energy of motion. And we already learned that the conservation law states that energy must be conserved. So we're trying to figure out how much energy needs to be converted from potential to kinetic, okay, because particles themselves also have potential and kinetic energy. The energy that's required to break bonds comes from the kinetic energy of the particles reacting or moving towards each other, and during that collision, that kinetic energy gets converted to potential. As bonds are broken and atoms are rearranged, that energy is changing. The amount of kinetic energy of a particle depends on its mass and its velocity. Okay, velocity is defined as the speed in one direction, but kinetic energy is dependent on both of those, velocity and mass. Some reactions actually just sit there for a little while before they have enough energy to react. If you remember Arrhenius, the scientist that came up with the acids and bases definition, he also coined the term activation energy. Okay, there's a diagram in your book that is really good about explaining it. The activation energy is the amount of energy for a reaction to even start. Okay, so if we look at this graph here, this diagram, we've got kinetic energy on the x-axis, number of molecules on the y, and you've got two different kinds of reactions. So at a really high temperature, more of the reactant particles have high enough amounts of kinetic energy. At low temperatures, this one right here, more of the reactant particles have low amounts of kinetic energy. Okay, so the amount of energy that's required for a reaction to start is known as activation energy, or how long it takes for a reaction to be activated. Once the reactants have enough energy and they actually start reacting, then bonds start breaking and forming. This is called transition state. And this transitional structure is also named activated complex. Okay, so these two are the same. Okay, it exists where the activation energy is the greatest, also known as EA for activation energy. And it's only after that transitional state is achieved and that activated complex is formed that the intermediate products can be formed. Okay, the intermediates again become reactants in the next process. Okay, and your book has a really good summary of that on page 737. So let's look at these two graphs and see if we can understand what it's saying. First of all, this is endothermic, which means it absorbs energy. Okay, so in this endothermic reaction, you'll notice I've got my reactants down here, and in order for them to reach that activated complex, it needs this much activation energy. Okay, so in order for the reactants to form this activated complex, where you don't really have reactants and you don't really have products, it needs to have an input of that much activation energy for it to produce products. Okay, and if we look at this next one, exothermic, we'll remember that exothermic means it releases energy. And in this reaction, it looks a little bit different, right? So the activation energy is really, really low in order to reach this activated complex. In fact, it's so low that in the end, it ends up giving off energy. Okay, that's why it's exothermic. But you need to know that this activated complex is an area where you don't really have a reactant or a product. It's transitioning into becoming products. And that's why it's called a transitional state. All right, so let's talk about what kinds of things affect how quickly a reaction happens. First, the nature of the reactants. What kind of reactants are they? Are they solids, liquids, and gases? 2, the temperature. We already know that temperature increases the rate of a reaction because it increases the energy and it increases collisions. The concentration, if we add more of something, that increases the likelihood of a collision to happen, increasing the likelihood of a reaction to happen. The surface area. If there's greater surface area, again, there's more exposure for collisions, which ends up making a reaction. Okay, this is why medication is given in capsules and tablets, but capsules are going to dissolve quicker because they have higher surface area. And a catalyst. We learned this when we were talking about equilibrium. Catalysts do not become part of a reaction, but they actually lower, the way they work is they lower the activation energy of the reaction. Okay, so your body has lots of catalysts in the form of enzymes. Catalysts work amazing to increase the reaction rate by lowering that activation energy. And here's a little bit of notes for what to expect on your upcoming quiz. I'll let you know when that is, so don't panic.